Welcome back, everyone. We're gonna today do some addition reaction, the last type. So what we have done is this: if you have some carbon chain with some sort of leaving group, then with a more unstable strong base, strong Lewis base, right? Mostly oxygen minus, or nitrogen even neutral or minus, or sulfur neutral or minus. They're able to attack carbon if it's possible. Then you get replacement going on. If that's not possible because it's sterically hindered, then you get elimination. That's the only thing you can do. Then if you eliminate, you get something like this or something like that. And we said this is a Hoffman, this is Zaitsev. Then you have to work from here in order to replace this, if that was the goal. Okay, so that's when you need addition. You want to add something, say here or here. You can choose those regioisomer, so you can add various things. Okay, something, let me just put it like X here, X there. You can choose, but you can replace this. So because the substrate was secondary and decent size of the chain doesn't allow substitution, but elimination depends on size. In Hoffman, relatively small, Zaitsev, then you need addition. Then you achieved substitution. Okay, this failed. So you want to add something over here, then you can do SN1, weak base, heat up, then this goes, charge here, shift, then base comes and top or bottom both attacks and racemization, but you get the attachment here, SN1. If you want SN2 here, which is this guy, then you have to do elimination due to the steric. Then you do addition this way, okay? And that's called anti-Markovnikov, anti-Mark addition. This one is regular Mark addition. And there are different functional groups we can add. You can even go back to this from here or even from there. Basically from here you add things right there, like anti-Markovnikov right there. From here you add it right there. So instead of here, so you can control where you put the things with different connectivity, regioselectivity. So this is the brief introduction about why we study addition reaction with the awareness of the connection with the substitution and elimination. Because eventually we have to build a new molecule, like I said, and we need to develop builder's eye, synthetic skill, not just mechanism or based on memorized reagent and typical type, figuring out what reagent you need and what product you get, or what reagent you need, what reactant you need to make a certain type of a product, those three types. But multi-step synthesis with back and forth connections or just a simple substitution when it doesn't work, how do you go through the elimination and get to the substitution you want? Things like those strategy becomes core skill in organic reaction. And there are only two, roughly speaking, two types of mechanism for addition. In order to have addition, you gotta have a pi bond. Two p orbital overlaps and create pi electrons with a 2 and 2 attachment, so double bond. Or you can have triple bond with these two p orbital overlaps, and perpendicular to this you can have another p orbital and make a pi bond. These two pi bonds, as you see, are perpendicular to each other, and the sp carbon has a linear rod shape of geometry, so the electron densities are here, and also they are front here and behind there, with the hydrogens or attachments, I'm sorry. So which one's more reactive? Obviously the carbon with sp hybridization make a stronger sigma bond, bring the two carbons closer, making attractions for the pi bond even stronger. So these pi bonds are more stable, attracted, and less reactive than the double bond. So let me introduce the two mechanisms of reaction using double bond. Let me first show you this type of mechanism. So this is the mechanism going through classical carbocation mechanism. So this classical carbocation will have SN1 like reaction. Okay, all of them. So that's first type I'm gonna show you. Out of that, you gotta have a control for the regioselectivity, which regioisomer you want to make. So regioselectivity is something you start to care. Okay? Then for that, you can add this type of a leaving group, or you can put this type of functional group. But fortunately, you can convert these to the better leaving group by adding H+. We talked about this. So, you can put H+ here and make a better leaving group here and here. You can do substitution with a weak base, or you can even do elimination and go back to this when you use a hard base like sulfate. Losing one hydrogen, the sulfuric acid has a strong negative charge, although with a resonance. With the heat, that stable base can act as somewhat stronger base. We talked about that, and that will be able to attack beta hydrogen, and you can get the double bond back. So it's good to remember H2SO4 with the heat, you can remove this, and you can add now to this way or that way. Obviously here you can eliminate them. Eliminate from here to get this, and from here to get that, E1 way, E2 way. But you can reverse that by addition. When you add, like I said just a bit ago, this with a nucleophile on the more substituted carbon, that's called the Markovnikov addition. When you add the nucleophile on the less substituted double bond carbon, that's called anti-Mark. So regioisomerism, and same for OHs. So the first typical conditions, just like SN1 need blah blah blah, SN2 need blah blah blah. You need to know what you need typically for these. So for this you need HCl, and that's it. And that one you need HCl with a peroxide and a bit of heating. This one, Markovnikov addition of OH functional group, you actually added OH with the one hydrogen here, because you know one hydrogen, there are two, right? You need H2O with H plus catalyst. That one is done in 2 steps, so you have to separate these two conditions by numbers, meaning step 1 will be completely done and isolate, purify, and characterize, and you reweigh the product to subject to the second step reaction. So these two are completely separate reactions. So if you forget putting numbers, you basically means everything here will be mixed up and it's not going to work. So the first step will be BH3. Second step, you need peroxide again and the hydroxide. Then you get this type of a regioisomer. Then a lot of variations possible out of these two. So these are the fundamental type 1 reaction, okay, with the SN1 like mechanism. But in that you have 2 different functional groups you can add in 2 different regioselectivity. So let me show you the mechanism of these 4. First, the pi electrons are here and they are unstable compared to all other sigma bonds, so they are acting as, you know, besides the lone pair, the pi electrons are second most reactive type, especially when you have permanent dipole like this. In the water, it will be isolated completely almost, because water surrounding H and the Cl and stabilizing them by solvation, that's stronger than HCl bond energy. But due to the solubility of these alkene, water is not usually solvent, so most likely they are together. So electron pooling, chlorine turn into negative, that means hydrogen is positive, so the electron here will be pooled. Okay. You may say, what if you have a base with a double bond? The base is not able to give electron to the carbon. If you do, then double bond breaks and electron goes to the carbon, and carbon negative product is not as stable as oxygen negative as a reactant base. So the conjugate base coming out of the Lewis acid, if it's possible, not as stable, so the reaction doesn't happen with the base. So double bond reacts with a normally acid with a good leaving group. So you do that. Then the thing is, hydrogen is really small, so the classical carbocation forms because hydrogen is a small acidic atom. So the hydrogen must choose where it will bound to. Will this make a bond with this carbon or this carbon using this pair of electrons? So hydrogen approach, the electron comes toward the hydrogen, but since hydrogen cannot hold electron with the somewhere in the middle of the 2 atoms, because no one is a positive here, so the electron on this side, not the hydrogen side, must choose where you want to have electron. So if I show you both possibilities, hydrogen comes here, then all the electron that used to be here is now stuck there, and positive here, positive there, pulling them, making this one lost electron and it stays positive. The other possibility is hydrogen comes here with the electron in the pi, then this carbon lost electron, so it's a positive. Then you know immediately the secondary is not the most stable. No, it's not only for SN1, E1. Whenever you form carbocation or radical, you ask same question. Most stable one? Say no, because there's a tertiary, so this will shift. So this one goes to this. There's equilibrium going that way. And I showed you before, this can react, but internal reaction, intramolecular reaction is faster, so this happens instantly. Then this has sp2 carbon with a p orbital, so top attack, bottom attacks possible. If these two groups are different from this and they are different each other, then the fourth one coming in will make this carbon, you know, chiral. So this carbon is a prochiral, but it's not, because they are same methyl group. So you don't have to worry about it in this particular case. So what is coming after first step? You know, you have a chloride. So chloride comes and you have, say, chloride comes from the top, then this group is pushed down from the flat shape, so they're together, and this is your product. But you know, you add hydrogen here, so you actually added hydrogen and the chlorine, so addition reaction is done through the classical carbocation. Why is it SN1 like? Because you have carbocation, just like SN1, top, bottom, sounds familiar, right? So yeah, that's one type of mechanism to give you Markovnikov. Then, presence of a peroxide, why does it make anti-Markovnikov? This is one of the ways of making the order of the reaction change. What do you mean? First, hydrogen add to the double bond. So hydrogen reacted first. So let's get rid of the hydrogen, make it unavailable for a double bond to react. How do you do it? You put more reactive chemical. And you see with the heating, what happens is oxygen, oxygen, with many lone pairs, the bond becomes weak compared to other sigma bond. Even chlorines and bromines and nitrogen single bond, they're all in the similar situation. These lone pairs stretches the bond, the sigma bond, and weakens it. Also, they are same electronegativity atom around the bond, so when you give a kinetic energy, you know, SN1, E1 case, the good leaving group go away by breaking the weak bond. Those bonds were weaker because carbon and the leaving group, bromine and iodines, are big, so it's easier to break. And this case, it's doing homolytic cleavage. You don't give both electrons to the one side, the leaving group side. This case, each take one. You see notice the usage of the arrow. There's only one arrowhead because you're moving one electron. These arrows are for both electrons. It's ionic mechanism. This is not ionic mechanism. Like I said, there are different ways of initiating reaction. So this way you can create two radicals to initiate reaction. So the electronegative oxygen with a +6 nucleus charge holding electron, and there is a 1 empty spot. Therefore, when this run into the HCl, H makes stronger bond with oxygen rather than chlorine. So this way, these two electrons are there and the hydrogens are full valence. So when this try to give electron to the hydrogen cannot just accept, so you have to kick one out. Then this one is gonna go to the the middle section of the two atoms, which is a bonding area where you feel most attraction around the two atoms, right? So if you do that, you're breaking bond and the chlorine becomes radical and you're forming water. So you have now chlorine radical instead of OH radical. An important point is there's no hydrogen on the HCl. It's chlorine radical that's more reactive than HCl. Although there is some HCl, chlorine radical just happen to be more reactive with the one empty orbital. So when the radical run into the double bond, this is what happens. It comes and one of the two goes. Then where do you put this electron? The chlorine should make a bond with one of the two carbons, and that's going to be sigma bond. But just like the carbocation, where you put the radical, do you want the radical to be on this one, which is a secondary? See, this one's a secondary with the two carbon neighbors, or you're going to put it on the tertiary, because 1, 2, 3 groups. So tertiary is more stable, so you put it that way, which means these two electrons must form a bond with this guy. You can review, it's similar to that. So the chlorine comes here and you have a radical on the tertiary. The other way around, if you put the chlorine here, radical goes there, then it's the same similar situation. It will rearrange. Then this radical is still reactive. They're running into some remaining HCl. Now this one run into the molecule, and carbon likes hydrogen. Always they like hydrogen. The bond is stronger, I said before. So arrow goes this way, showing two electrons are coming between hydrogen and the carbon and start to get closer and form a bond. As you break this bond, taking them away, one to the hydrogen side, one to the chlorine shell side. Therefore, you have a chlorine sitting here on the less substituted and hydrogen on the more substituted. It's the opposite. It's anti-Markovnikov. And you have a radical, so you can continue. This act as a radical, run into another double bond, and this keeps going on. This is called radical chain reaction. So as you see, these two are putting chlorine with a hydrogen on the double bond, but different way. They switch the order of the reaction to give anti-Mark, the regular one. So we are working on this one. and we took care of this. Now this case, this first example is rather similar. So you have a partial acidic hydrogen, partial basic oxygen, which is initiating reaction. This is most attractive. The base is not able to give electron because you end up making carbon negative, so you don't. And this partial plus is not able to accept electron. If you do, you have to break off the bond by giving electron to the oxygen, and oxygen minus is not as good. So the best is this acid without the leaving group, or even with a good leaving group like HCl, fine, and it's able to react. Then you know, same, the hydrogen is small, so you create a classical carbocation on the more substituted carbon. That's a better, stable, more abundant intermediate. Then SN1 like, but only base you have is weak base of water. You know, it's similar to SN1. SN1 case, you can use water, but also you can use alcohol, right? There you can use alcohol as well instead of water. Then you come up with the ether as a product. You can use a lot of different bases and come up with all sorts of different functional group added to the double bond. So since these two are same groups, you don't have to worry about coming up with different stereoisomer. So water just add. I will not spend time describing stereoisomers. So you got this. Then I said, you know, when oxygen is positive with hydrogen on it, it's not stable. I mean, it's very acidic basically. So some conjugate base or solvent comes, takes the hydrogen, then the water become OH and hydrogen go away, electron become lone pair. Then you have addition done, Markovnikov addition of OH. So alcohol, if one of the H was R, right, then this will be R, H is gone, so this will be R, you made an ether, and you can imagine all kinds of functional group, and it doesn't have to be always oxygen too. So those side items you need to keep thinking about it, because eventually all of these fundamental mechanisms will be used to synthesize. And organic too is all about multi-step synthesis with the spectroscopy to confirm and monitor the reaction. So Markovnikov reaction is done. I'm just trying to expand your understanding. And anti-Markovnikov addition. First what we did was BH3. Sometimes this is written as THF with the two pairs. What it means is basically boron with a 3 bond as sp2 with a p orbital. We talked about it. Doesn't exist that way. It actually stays as a tetrahedral when the solvent make a bond with the two lone pairs of oxygen. And it becomes negative though. That makes these hydrogens even more partial negative. You know, hydrogen's more electronegative than boron we talked about. And this oxygen is part of the tetrahydrofurane, which is this guy with the 2 double bond. It's furane, but those accepted 4 hydrogens by reduction reaction. This is a THF right here, and oxygen turned into the positive, and that is the active form of BH3 hydroborane. And originally hydroborane is in dimer form, so B and the B shares 2 hydrogen and having tetrahedral-ish rearrangement of the 4 additional hydrogens in the dimer, and this breaks apart by the solvent when solvent try to interact with the acidic, partially positive acidic boron. So when you have this gives electron to the partial positive boron. Okay, this step is conservative, but I'll just show you as a stepwise mechanism to explain and make you understand the mechanism better. So the pi electron rushing to the B, and again electron cannot stay in the middle of the bonding. They must be attracted by at least one atom, so it goes here or here like we did before. More substituted carbon should be positive, so the electron must go here and make a bond with the boron. So the boron comes here, accepted electron negative with a 1, 2, 3 hydrogens, and they are big negative, and the negative here decrease. This is just the formal charge. The actual charge is not fully negative. Electrons moved away to the hydrogen. This is a positive. And then intramolecular interactions faster. So as you see, these basic hydrogen using its sigma electron, not lone pair, not pi. You see the sigma electron. That means the bond will be broken, and these two will be staying between carbon and hydrogen, meaning forming another covalent bond. So surprisingly, your anti-Markovnikov intermediate is already formed. Again, in this process, you changed the order of the reaction. You didn't have a hydrogen reacting first with a double bond. You had another one did. This time, it wasn't by having more reactive chemical take away hydrogen and make a more reactive chemical, but rather you put the opposite charge on the hydrogen, not positive but partial negative, so it doesn't react, because negative, the base cannot react with the double bond because the product was not possibly stable. So that repeats twice more here with 2 more double bonds, twice more. Then you get 3 of those bound to the boron. Okay, so boron basically has those 3 ones in sp2. Then second step starts. H2O2 OH minus. This mechanism, I'll leave it for the B level. This eventually replaces the boron with the OH, not this OH, it's from one of these oxygens. But anyway, you get the oxygen H there, and you have an anti-Mark. Hydrogen's already added there, so anti-Mark. So that's enough mechanism for you, because you can understand anti-Markovnikov product. So these are the all similar type of and relevant chemistry through one similar mechanism.